All right, hello everyone. We are here with a video that will cover the solutions to the midterm. The midterm has questions 1 through 6, so we will walk through, try to do it reasonably, walk through each of the solutions to each of the problems. So let's get started. So number one starts off, and I'm going to read the questions aloud. Says given t of n equals 16t n over 4 plus n squared, and then we have a. So a is use the master theorem to find the asymptotic bounds. So we're just going to start right off with a equals 16 from the formula that we have. B equals 4. And f of n equals n squared. So if we plug that in, log b of a, we see that that is equal to 2. So as you can see here, I'm hoping this shows up. Yes, it does. If I highlight that, we put in there, and now we have n squared because log b of a equals 2. So we see that it equals to f of n. So therefore, we know that we will use case 2, which tells us t of n is equal to big theta n squared log n. So now we will move forward with the substitution method. With the substitution method, first, the first step, I just have copied the question there. And this is our guess. So I will put that there, and I just chose n squared log n just because we did solve it first with the master theorem. I hope that's okay. So next we continue with the substitution method. The next step, we have 16c n over 4 squared log n over 4 plus n squared. And now continuing after working that out, we have t of n equals cn squared log n over 4 plus n squared. And then we have t of n plus cn squared log n minus 4 log 4 plus n squared. And next we have t of n equals cn squared log n minus 2 plus n squared. Next we have t of n equals cn log n minus 2 cn squared plus n squared. Excuse me. Next, we have the final step, Tn equals Cn squared log n plus n squared. And then in parentheses, you see right here we have 1 minus 2c. So in order to move forward, we show we solve for the constants. So which is c. So we see that 1 minus 2c. If we set that equal to 0 and we solve, we see that c is equal to 1/2, and thus we excuse me, we prove that t of n equals big theta n squared log n. I apologize. I converted this from Google Drive, so I've kind of actually had some problems, and I really hope it will go away. Let's see, log n. There we go. So now moving on to number 2, using the master theorem, which is like part A of number 2. It says given t of n equals t of 3n over 19 plus 5n, and use the master theorem to find the asymptotic bounds. As we see here, I've just copied the problem down, and kind of like A in number 1, we just go through and we use the formula, and we find A is equal to 1, B is equal to 3 over 19, which does, that's definitely one that I haven't seen before. It doesn't necessarily make it more complicated. And f of n equals 5n. So next we plug it in, and we see that log b of a, we get is 0. So we have n 0. So up here, we see that, excuse me, we see that we're going to have to, this is n up to the first power, so we know that we must add, so we know that is case 3 for epsilon that we will need to add. So then for case 3, we have the second part, which is AF B over A is less than or equal to CFN, which then we have 9, which comes out to 95 over 3 is less than or equal to, excuse me, 5C, which holds true for C is greater than or equal to 19 over 3. And finally, we see that T of n is equal to big excuse me, big omega f of n is, and finally is equal to big omega 5n. So moving on to number 3. We have number 3. I'm going to read the question out loud. Assuming you have a task to sort telephone numbers of a major carrier, what sorting algorithm will you use? Please justify your answers. So with this one, we go back to the top of this page. I apologize. There we go. So I just wrote radix sort here just in case we just for the answer and then the explanation. So one thing I thought about with this one is there's a lot of external factors, like what if you have some memory requirements, and I may have not needed to go into that, but hopefully that's okay that I did. I still get down to the the answer toward the end, but I just wanted to really go through my thought process on this one. So if we just kind of think about the data set in general, so if we have a telephone numbers of a major carrier, first thing that comes to mind because of major carrier, we know it's a large data set, and we also know the format, like we know what phone numbers look like and so forth. So we use that to help us to determine what algorithm to use. So first thing I wanted to just start with, which may be unnecessary, but we know that heap sort, merge sort, and the other comparison algorithms, I didn't list them. They achieve the lower bound of big O. They have the lower bound of big O of n log n when sorting numbers in worst case, and quicksort has that on average. So and these comparison algorithms are determined on the comparison they use that is determined using the input elements. So the one is compared to the next one and so forth. It doesn't have a defined, it only depends on the elements that are inputted into the algorithm. So with that being said, I just want to cover that real quick. We're going to explore the other options. So counting, radix, and bucket sort are all run in all linear time, working with numbers. So we're going to check. We take a look at those, and we do expect those, and they do outperform the others. I would use one of these algorithms to sort the phone numbers. So determining which one I go and I talk about here. Neither counting sort nor bucket sort is sorted in place, and therefore there's a lot of overhead. So let's say I know this isn't in the question, but this is one of the reasons, kind of like a point for radix sort, for example, because neither excuse me, neither counting sort nor bucket sort is sorted in place. So if you did have a memory requirement or a limit for say, these are neither sorted in place, so radix sort would kind of be get a point compared to those two. And as well, another reason we can count out bucket sort is because of the worst case running time of big O of n squared. So therefore, I feel like radix sort, with its along with being stable, is superior algorithm for sorting phone numbers compared to the counting and bucket sort. So moving on, I'm going to do my best to walk through this code. So please, number 4 is please revise the textbook pseudocode for merge sort and merge functions for your merge triple sort algorithm. So just a background, the book gives us merge sort and the merge function, the merge function. What we have to do, originally they divide into 2 separate arrays, and that is called recursively. So what we need to do is, for this question is, for merge sort and the merge function, we need to transform those to allow it to divide into 3 arrays. So give me just 1 second here. So merge originally, that is this function here. I call it, I hope the name is okay. Merge originally has A, P, Q, and R. Now, I wanted to go into these. A is just the array to be sorted. P in the original array, the original merge, you have P, Q, and R. P is the starting. Q is it is calculated in the merge sort and passed into the merge function, but usually it divides it in half, and I believe it rounds down. And then usually we have just R, which represents the end of the array, the end of A. But in our algorithm, because we have 3, we will have 3 different arrays. We have A, the array to be sorted. P is still the beginning. Q and R are indices, though, that divide it instead of in half, it's in thirds, and we have S as the end. So we start off and we calculate in 1, in 2, in 3, just like the regular merge algorithm, which calculates in 1 and in 2, which calculates the starting position, or excuse me, I'm sorry. This, let's see here. Yes, I'm sorry. This will compute the end index for each of the arrays. So for here, also in this book, I get a little confused because sometimes they use 1 versus 0. So I tried to keep that consistent as well. So if you look here, we initialize L, M, and R. These are the 3 arrays that we are going to split A into the first time, which this does get called recursively. We have Q minus P. I wish I had some visualizations to make it easier for everyone to understand. But Q, again, is the second, the beginning of the second array. I just want to make sure I said that right. Yes. So we take the beginning of the second and minus the position of the first, the start of the first, plus 1. So if we had this possibly could be 0, and Q could be 3, for example. We would have, or excuse me, that's not correct. It is Q. Yes, Q minus P plus 1. Yes. Okay. Let me just make sure if that's okay. Yes. So, oh, okay. I'm sorry. Yeah. So Q minus P. That was right. I'm sorry. So Q minus P, if that's if Q is the beginning, and what we need to be able to do is find the end position. So, for example, P, say we start at 0, and this Q starts at 5. We see that P minus 0, or sorry, excuse me, 5 minus P, or excuse me, P would be 1. I'm sorry. Q minus, if Q starts at 5, we have 5 minus 1 plus 1, so we know that N1 is 5. So here, when we start the left array, we know that it goes from 1 to N1 plus 1. So that is the end of the left array. And then here we have 1 plus 1 to N2 plus 1, and 1 to N3 plus 1 for the right array. Sorry, that took me a minute. This just kind of gets confusing without the visualization. And like we talked about before, S is the end, so R is the beginning of the last array. So here we have the total minus the beginning, which gives us the total length. So for example, each one of these would be maybe length of 4 if we had a total list of maybe 12. So for the first loop here, we have 4I equals 1 to n. So for all integers, for all the elements, we take the left. We do actually do this for each of the arrays. I'm sorry. We have the left array, which is called L, and for each element, we grab we add the values, from the array A into the L array. So now, if we look at the next one, so this is to N1. I didn't, for some reason, I didn't mention that. So N1 again is going to be the length of these arrays. So like we said, if there's a total number of 12 for A, each one is the length of 4. So this will loop 4 times, and we grab for the left array, the first 4 elements, for example. And the same with these 2 steps. So for J and for K, we go to N2 and 3, which are the length of those arrays, and we add them into the middle. We get the values from A and add them into the middle, and the values from A and add them to the right. So this just sets up the sentinel value. This is pretty much the code from, this is very similar to the code in the book, except for we had to add 1 array to the end. And same thing here. These are just indexes we will use. So this last, this last for loop, this is where we actually start to compare them. What we do here, so if the value in Li is less than Mi, we now check to see if Li, is less than or equal to Rc, which Rc is just the C is just the index of the right array, which currently they're all at 1. So I like the example used in the book. Imagine we have 3 sets of cards with the cards facing up, and our goal is to sort them and put them into 1 stack facing down. And we only set the cards down when they're the lowest on the top. So again, if Li is less than Mj, and if Li is less than Rc, we take the card and put it face down, which here is where we take the value out of Li that is less than all the other cards facing up, and we move them into AI. Now, our next goal is to sorry, I need to. We increment I here because I was the indice of L that we actually, for example, we put the card face down, so we increment that one. Now, if this condition does not hold true, if RC is now the smallest, we know because of just the flow of control that RC would also be less than MJ, so we know it's the smallest, so we add it back into the original array, and we increment C. And then down here, this else statement just comes from up here. So if Li is not less than MJ, we know that MJ is less than than Li. Then we test to see if it's less than RC. If it is indeed less than RC, Then we add that into the array A, the sorted array, and we increment J. And then here at the bottom, we again, if this does not hold true, we add RC into the array, and we increment C. Now the second part is the merge, the merge sort method, or excuse me, algorithm. So this is what calls this. So here we have A, P, and S. P is the beginning, S is the end. Sorry about that. So here we check to see if the array is empty. If it is not empty, we move forward. We calculate Q. Now, because in the question it did let us know that we did not have to worry about the situation where n is not divisible by 3k, so we know that it will be 3 equal sized arrays. So here we just divide. So we do, so Q Q is going to equal the it divided into 3 different arrays. So we're gonna find basically the Q, if you remember from the method above, right here is the beginning of the second array, and R is the beginning of the third. So what we do is we take Q Q plus S divided by 3. Let's see here. Let me just make sure that is correct. I did write that most of this down in paper and converted it, so I always get nervous that I wrote something down incorrectly. Let me just make sure here. That was supposed to be P. I knew that was wrong. So P plus S. So this is just going to be the total divided by 3. So if we have a length of 12, the Q is going to equal 4. Now that gives us the starting point of the second array. Now we need the starting point of this third array. So we get R, and that's 2Q. So for example, we'll have one array starting at the beginning, P, and then we'll have Q at 4, and then the last array R starting at R, which would equal 8 for the example of 12. Then we just call the merge sort 3 times, which is where it's split into 3 arrays. First array is let's see, P to Q, and then the next array is Q plus 1 to R, and then the last one is R plus 1 to S. And then finally we call the merge, which is what we are familiar with from above. So the second part is find the asymptotic bounds for the running time of merge sort. So if we look at merge sort, we see that triple merge sort is called 3 times, which is, I just wanted to point this out, is recursive and divides the array into 3 separate arrays, which would then be sorted. So once we split the original array, we split each of the 3 arrays into 3 more arrays and so forth, because it is recursive. So in the end, we end up creating 3 subproblems of size NB in dn time, which is where B is equal to 3. And the merge step is done in constant time. So what I mean by A here is A is just in the function that the formula we're familiar with. I just want everyone to know that this is where A comes from, and this is where B comes from. So in the end, we create 3 subproblems of size NB. So this B is equal to 3 as well, and the merge step is done in constant time. So that's how we come up with these numbers here. And this number here. So we come to T of n equals 3t n over 3 plus n. So we solve to find that the asymptotic bounds is big theta n log n. I also wanted to show my work here. So right here just kind of shows, using the master theorem, my work. Next, number 5, we have we modified the pseudocode for the count sort algorithm on page 195 of the textbook, such that input array numbers of range -n to n can be sorted. So this one took me a while to figure out, but I finally figured it out. So count sort, we have the original array A, excuse me, and the array we would like to add the A into, and then the max range of K. So because we're using the -n, we have to create something called the minimum value, which I said equal to 0, and then then we iterate through A and figure out the minimum value, which includes negative values. So now what we're going to do, for example, let's say the minimum value is -3, and we passed in 3 for K. Now we see right here, we're going to create this K up here for this, because we're using negative values compared to the original algorithm, we create new K, which is K minus min. So for the example I just used, we would have 3 minus -3, which would be 6. Now we initialize D, and now we fill D with we iterate through. I just used this because this is also in the original algorithm in the book. Next, we add we add the values in A to D and transform all the numbers. So this is the main part. This is the other main part. Besides finding the minimum value of the negatives, including the negatives up here, and creating this new K, what we do here is for every list, so we're going to add every value in A into D. But what we're going to do is when we add them in there, what we are going to do is subtract the minimum value. So let me just pull this up here. Let's see, where did I put that? Yes, so we subtract the minimum value. Sorry, I'm trying to find where I put. Here it is. Okay. So now, like I was saying, we contain. We add into the array D all A minus the minimum. So now we this array D now that we filled up with the values minus the min, which we know is the lowest number. We can now act like, for the time being, since we transform the numbers. So, for example, for each of these, we see that 6, the value 6 minus -3 would become 9, and so forth. Let's see. And the way what this does is basically get rid of our this transforms them to get rid of the negative values. So now we initialize C, and now we filled the empty list, and what we do here, what we do is we count the. Let's see. I want to make sure I say this correctly. Let's see. What we do is we make a list where C I contains the number of elements equal to I. And this right here, what this will do is allow CI to contain the number of elements less than or equal to I. So if we remember the visualization from count sort, or counting sort, it really helps us view this and helps me view this as well. This right here is basically where we go through and we count the values. If you remember how counting sort works, everyone, that we just go through and we count the values, and then we put them in that index. So if we count 3 ones, we put them at index 1. And now moving on, we have this method here. And this actually, this one right here is where we add them into the final sorted array. This is just where we convert them out, kind of as the out of C and into, and this is the final step for actually sorting them. Now we have sorted the numbers that we have, but don't forget that we transform the numbers. So now we must transform them back, and that's what this final step does. We just add them in back. It's like if it was, for example, we had the example of 6 earlier, or it would be 9 after it's been transformed. We would add -3 back and it becomes 6. And we just add those back into the position it is in. All right, so our last question, we modify bucket sort the pseudocode on page 201 so that can sort floating number in range of -50 to 50. So this one was one of the more difficult ones for me just because it didn't click right away. But basically what we do is, because we have the negative numbers and we have the floating point numbers, what we're going to do is we're going to transform them all. And because the algorithm's pretty much the same, I'm just going to go over the main steps. Besides us having an extra array, what we do here, sorry, let me just find where, here it is. So once again, before we sort and create the buckets, right here is where that is done. Here is the extra step. We just transform all the elements by AI divided, so each value divided by 100 plus 50, because we know that it can only be -50 to 50, and what this does is it transforms them into the correct out of negative, for example, and it helps with dealing with the floating and non-floating point, or the regular integers. So if we take, for example, I'm just going to type down here 35 right here, and we divide that by 100. I grab my calculator, sorry, which this part is easy. So 35, or excuse me, I'm at -35. -35, and we do that divided by 100, we get and then what we do is we add 50, which gives us -49.65. Okay, so now, excuse me, not negative, I apologize. So 49.65, which is a positive number, easy to work with, and so forth. So now, imagine we did this with all of our numbers, and we have numbers like this. They're all positive, so what we will do is we will sort them all. And now this step right here is where we actually pull them out. I mean, excuse me, transfer them back to the actual number. So after they're sorted, what we do is right here, as you can see. So let's just walk through that. So let's say C of I is equal to 49.65. And now we do -50. Oops, excuse me. Which will equal -0.35, and we multiply that by 100, which will give us our original -35. So that's the transformation process. Those are the main steps I added in here. I hope I explained it all right. If you go to this page, it's easy to see the original one, so you can see how it changes, and I think that'll make much more sense for everybody. Let's see here. I believe, like I said, in this step is where we actually append each of the lists at each index into the final sorted array, and then we transform them. So along with this step and mainly this step, these are the main additions to this array, besides maybe overhead overhead for creating the arrays that we need to use and so forth. So that is it. Thanks everyone for watching, and have a great day. Thank you.